This is the continuation of video lecture on IC 555 timer and its application. In the last lecture, we learned about the architecture of 555 timer, and we listed the applications of 555 timer. And this 555 timer is operates in different modes, that is monostable, astable and bistable multivibrator mode. So today we are discussing on monostable multivibrator using 555 timer. So here for that you can see I have taken 555 timer IC diagram, and on the left side you can see it is monostable multivibrator using 555 timer circuit diagram. So you can see all the 8 pins here on 555 timer, and you also know the 8 pins of 555 timer. The only additional components what you can see here are resistor and a capacitor, nothing else. And these resistor and a capacitor are connected between pin number 8 and 7. Okay, 8 and 7. What is 8 and 7? 8 is VCC, correct, and 7 is discharge. Okay, and you can see capacitor C is connected between pin number 6 and 1. 1 is ground, 6 is threshold, right? So if you do connections of this type, this becomes a monostable multivibrator. Basically, monostable multivibrator, it is called monostable because it has a single state. Okay, it is by default having a low state, so single state. Whenever a triggering input is applied to pin number 2 of this IC 555 timer, then it will change its state from 0 to 1, and it is not stable. Okay, after a certain time again it will come back to 0. So 0 level is a stable state for the monostable multivibrator. So and it is the only state it has. Other state, it is the not stable state, is the unstable state. Okay, it is intentionally made. Okay, that is how you are able to produce a pulse of desired width. Okay, 0 to high, and high it will retain for a certain time, and that time is decided by R and C component what we have in the circuit. Based on the RC time constant, the duration of pulse is decided. Duration of pulse means how long the output of this 555 timer is in unstable state, that is at high state. Okay, before it go to the low state, how long it takes, okay, to remain in high state. So that is decided by the values of R and C, right? So we can better understand this circuit with the help of internal architecture of 555 timer. Before going to that, let's see here pin number 4 is connected to VC. What is 4? 4 is a reset pin. Okay, so if you have nothing to do with the reset operation in this 555 timer, so you can connect it to VCC, so you cannot do any reset operation in this circuit. So that is why 4 is directly connected to VCC, as we discussed earlier. And you can see 5 is a control voltage. Okay, this control voltage is an additional feature what this 555 timer is having, wherein you can change the threshold values, okay, in the resistor network what we have in 555 timer IC. So usually if it is in monostable we won't use that, and it is connected to ground through a capacitor. Okay, so in order to adjust any spike noises and all, we use a capacitor. So this pin number 5 is directly to ground because we are not using this control voltage, right? So, and triggering input we have at pin number 2, and output. Okay, that's it. So let's take this monostable multivibrator in detail. Okay, this is the monostable multivibrator, considering the internal diagram of 555 timer, you can see this is a 555 timer which we discussed in the last lecture. Okay, this is the voltage divider network, 5 kilo ohm each and 2 VCC by 3, 2 VCC by 3, value divided, and comparator section we have, one flip-flop we have, power output we have, discharge unit we have, right? Anyway, in this particular case, this reset 4, pin number 4 reset is connected to VCC. We are not using it, right? And control pin number 5, right? This one, pin number 5, it is connected to ground through some capacitor. It is connected to ground. It is not shown here, but it is connected to ground as we saw in the previous diagram. You can see here control is connected to ground, right? Okay, you cannot left it open, right? If you are not using it, doesn't mean that you should open it, left it open, because it is undefined state, high impedance state. You should connect it to VCC here and this should be connected to ground. So only additional components now we have in this monostable multivibrator is a resistor RA and a capacitor, right? So internal operations remains same, fine. So let me explain this starting from here. Okay, so whenever a triggering pulse is applied, please make sure it is VCC and this is 0, and we always consider rising edge 0 to VCC, right? This is negative going pulse, but we consider 0 to VCC case, right? Means rising edge of this triggering pulse. So whenever it goes from 0 to VCC, in between it will come across VCC by 3 at some point. So whenever it crosses VCC by 3, okay, output of this comparator becomes 1. When output of this comparator becomes 1, that is lower comparator, this is S and this is R, this is RS flip-flop, correct? And the flip-flop output goes to high state. So Q is equal to 1, but we are using Q bar, right? So this is Q bar. So if Q is equal to 1, Q bar equal to 0. So 0 is connected to this, and this is a line driver, right? It is inverted driver, and if it is 0, output is 1. So you get a high output voltage here. Whenever a triggering pulse is applied, you get a high output voltage. Okay, right? And it will stay for a long time, right? And it depends upon the value of RA and C. How? Right. Now, so see, whenever triggering pulse is applied, Q bar is equal to 0 and output is 1. Q bar is equal to 0 means this transistor is in off state, right? So there is this transistor is in off state. So there is no connection between the collector to emitter, so that your capacitor is charging already, okay, through a resistor RA, okay, to a maximum value of VCC, right? Capacitor charges, okay, right, through RA, got it? So this process continues, but at some point of time, as we have one more comparator, upper comparator, and one terminal of which is 2 VCC by 3, whenever the capacitor reaches to a value of 2 VCC by 3 or just about 2 VCC by 3, this comparator will produce high output voltage. Please remember, this will produce high output voltage, right? And this is R, flip-flop input R, reset pin of a flip-flop, okay? So when R is equal to 0, output is also 0, but Q bar is equal to 1. When this becomes 1, okay, output becomes 0, right? Output becomes I to 0, it's I to low, 1 to 0, right? So whenever it is 0, please remember this transistor again goes to off state. This is 1, this is 1, okay, this is 1. This transistor goes to on state, and capacitor will not completely charge to its maximum value of VCC. Whenever it reaches 2 VCC by 3, alright, it starts discharging through this transistor, and the potential at this point will be 0, right? Potential at this point will be 0. So it will, initially it is at low potential, output is at low potential. Because of the triggering pulse, it will go to high state, and it remains high state until the capacitor voltage reaches VCC by 2 VCC by 3. So that comparator becomes 1. That means reset equal to 1. Output Q is equal to 0. Q bar equal to 1. So this transistor will turn on. So capacitor start discharging. It will not completely charge us to its peak value, right? That is VCC, right? Whenever it is 2 VCC by 3, it starts discharging because of this action. Okay? Output will be 0. So low to high, then after some time high to low, and output remains in the low state until one more triggering pulse is applied. Right? At what time triggering pulse is applied, it all depends upon the application. Right? So for the next triggering pulse, again this comparator will produce high output voltage, and this is a set pin of flip-flop. Q is equal to 1, Q bar equal to 0, transistor is off, capacitor charging. If it is 0, output is 1. So when triggering pulse is applied, output is 1. Transistor is in off state. Your capacitor charges to starts charging towards VCC through RA. Right? Whenever this charge across the capacitor reaches 2 VCC by 3, output is 1 here. The reset pin equal to 1 of a flip-flop, output is 0. Q bar equal to 1, output is 0. When Q bar equal to 1, transistor will on and capacitor start discharge. So this process continues. Okay, whenever you need a pulse output, one has to apply a triggering pulse, and duration of that pulse, output pulse, right? Duration of the output pulse depends upon the RC time constant. The same thing you can see in the waveform. Whenever a triggering pulse is applied from low to high pulse transition, okay, your capacitor starts charging. It starts charging. Okay, don't forget about the dotted lines what you can see here, right? Capacitor starts charging. Output is low initially, it becomes 1 immediately. Okay, whenever there is a negative triggering pulse, output becomes high, right? And it stays high until your capacitor voltage reaches 2 VCC by 3. Whenever it reaches 2 VCC by 3, okay, output becomes 0, right? So 0 to 2 VCC by 3, that is the capacitor voltage, right? This capacitor voltage always switch between 0 to 2 VCC by 3, right? And also you can see how many number of triggering pulse you apply, okay, between this 0 to 2 VCC during the charging period of capacitor. It doesn't have any effect. If you whether apply 1 triggering pulse, 1000 triggering pulse, it really doesn't matter, okay, during the charging phase of it. Okay, this phase will change from 2 VCC to 0 only when your capacitor charging voltage reaches to 2 VCC by 3. Then only output of this 555 time will go to 0, irrespective of number of triggering pulse you apply. It really doesn't matter, right? And also you can see dotted line that shows as and when you apply a reset value from VCC to ground, means 0 volt. Okay, irrespective of the condition of the capacitor, whether it is charged to VCC 2 VCC by 3 or VCC by 3 or any 1, 2, 3, whatever the value, it will come back to 0 and output again come back to 0 immediately without any waste of time. This is about the monostable multivibrator. Yeah, you can see here VC voltage across the capacitor is equation is VCC into 1 minus e raised to minus t by RC. That is how you can express the voltage across the capacitor. When that voltage across the capacitor reaches 2 VCC by 3 and at time t is equal to t, okay, this is the equation what you get after simplification. T is equal to 1.1 RC. This is the equation one has to remember, one has to understand in order to solve problems on monostable multivibrator. Okay, 1.1 into RC. One simple problem on monostable multivibrator. R is given for a monostable multivibrator. R is equal to 100 kilo ohm and time delay is given. T is equal to 100 millisecond. And here it has been asked to calculate the value of capacitor C. So for this you should know the equation. T is equal to 1.1 RC, where R is given, T is given, you can calculate the value of C. It is 0.9 microfarad. After the calculation you can cross check this later. So this is about the monostable multivibrator. The application of monostable multivibrator, you can find the missing pulse, you can generate a ramp, frequency divider, pulse width modulation. So these are the applications of monostable multivibrator, how you can use this monostable multivibrator in different applications. And explanation of the same is also there in the slides. So for more information about the monostable multivibrator, you can refer these slides. We'll share this with you later, right?